Hey everybody, we are going into lesson 11.4, three-dimensional solids. Now we're getting somewhere. We have some specific shapes and different definitions that we're going to define here. So it's a lot more of the geometry that you've been kind of looking for most of the year with 3D objects and just defining different parts of a 3D object, which will be important. Polyhedron, some definitions. Polyhedron, a solid that is bounded by polygons called faces. So if you're looking at that bottom right-hand corner shape, right, the polyhedron there, each of these shapes are, each of these shapes are, right, a face. This would be a face. This whole thing would be a face, right? And we have a square up here. We have a trapezoid looking thing up here, but we're just going to call it a quadrilateral and things like that. So this would be a face over here in the back, right? That's another face. And so what we're going to do is we're going to count how many faces, count how many edges, count how many vertices, vertices, whatever, that we see in the image here. An edge, right, going into this one. An edge is the line segment formed by the intersection of two faces. So if we're looking at the edges, we're looking at this right here. This would be an edge. This would be an edge. This would be an edge. And so we count how many edges that shape would have. A vertex, I'll put that in the orange, is a point where three or more edges meet. So 1, 2, 3. It's all the points, right? So these are all vertices, vertex, a vertex, a vertex. All those are vertex. And sometimes we're going to have to count how many faces, edges, and vertices that we see in the three-dimensional solid. If you missed any of the definitions and you wanted to write them down, obviously you can pause and go back. But the question is, are these polyhedrons based off of our definition? For sure, yeah, this one would be a polyhedron. It's got faces, edges, and vertices. Mainly, though, it has faces. So yes, this is a polyhedron. However, if you ever see curves, if you ever see a circle, that is your big indicator that, man, you do not have a polyhedron. We need flat sides. We can't have any curves. We need faces. We need edges. We need vertices. So this one would not be a polyhedron. Unlike that, this one has no circles, no curves. So this is a polyhedron. A cylinder would not be a polyhedron. So pretty straightforward on those fronts. Of the 5 solids below, the prism and pyramid are polyhedra, right? So like we were defining before, the cone, cylinder, and sphere are not polyhedra. Anything with curves, like we just said. Here's some more definitions. A regular polyhedra has all the faces that are congruent. So we would say that a regular triangle, right, has everything that is the same, right? Angles, sides. And so it's saying that all the faces are also the same, equilateral, that kind of nature. Okay, so that would be a regular polyhedron, a triangular regular polyhedron. A convex polyhedron, we've seen things like this before where there's no cave-ins. Everything's kind of just a normal, you can almost say this is the normal looking one. All vertices are point outward. But the weird ones would be the concave, where it's caved into where you'd think it would not be anymore. Some vertices point inward. And so it's like kind of cutting into the shape, just like this would be a concave shape, right? This would be the concave polyhedron. Another interesting little tidbit here, and you see this a lot in engineering where you're working with planes, and even at the beginning of the year we talked about planes where it cuts into a shape. Cross section is what we call that. that little plane, and that's the intersection of a plane and a solid. Plane and a solid. So when it asks you, when we're working with cross sections for our purposes, we're just going to describe the shape that's formed when you use that cross section. So in this example, the cross section creates this shape, and this shape looks like it's a circle. So that's what we're going to call it. So for letter A, if we're truly working with a cube and we have something like this kind of cross section, we could call it a square, right? But if you're being more generic, you maybe don't know it's a quite a perfect cube kind of idea, then we just call it a rectangle. Come on. There we go. Right. This one's a little tricky. It looks like it's going to be a trapezoid. However, let's count how many, right, in a different color here, how many sides we have. 1, 2, 3, 4. See how it's cut kind of funny there? And then 5. So we'd call this not a trapezoid. We're just going to call it a pentagon. Okay, it's not a trapezoid either because it has 5 sides, not 4. And just leave them like this. Just call them a rectangle, call them a pentagon, call them a hexagon. Try not to use some of the other vocabulary like rhombus, kite, things like that. Just use these kind of words. Let's see what the cross section looks like here. Now, you have to kind of use your imagination here a little bit, but here's one of the lines, right, that it's crossing into. The purple. I'm looking at the purple right now. If you're looking at the cross section of the picture. So here's a line. Oh, here's that line. Here's the third one. So this one looks like it's going to be a triangle. All right. Very good. Platonic solids. These are just more, that's kind of more vocabulary on our polyhedrons here, being more specific behind what different shapes you have that are more used. Regular tetrahedron, kind of it's almost like no one ever uses that kind of vocabulary, but in math, that's what we're going to use. And these are commonly used in either math or other kind of places. These different kinds of shapes is 4 faces, 4 vertices, 4 edges. Cube, you've seen a cube before, like dice. And so I almost think a lot of these are kind of like dice. Sometimes you have a 4-sided dice. Sometimes, right? This is a 4-sided dice. This is our normal 6-sided dice, right? And then this is, you could guess, right? 8-sided dice, 8 faces. And there are things such as 12-sided dice and even 20-sided dice. People use in games or Dungeons and Dragons and things like that. But these are Platonic solids, and they should be even on all sides. Right? Cubes have 6 faces, 8 vertices, 12 edges, and all of these different kind of definitions that you already have in your notes there. So I'm not going to talk about them too in depth, but these are more commonly seen polyhedrons that are should be equal on all sides, right? Because they are regular. Sometimes you might need to name them. So that's just a good thing to know. Euler's theorem. It's actually Euler's theorem, but the number of faces, he just created this little equation we can use here to figure out how many faces something has, how many vertices something has, if we have the other 2 variables, right? So there's a formula for that. If you have the faces and the vertices, you can find the edges. It'd be faces plus vertices equals the edges plus 2. So here are 2 examples using that. The solid used here, right? This one right here, has 14 faces, 8 triangles, and 6 octagons. How many vertices does the solid have? Now, technically, there are 2 ways to do it. One, you could count 1, 2, 3, 4, 5, 6, how many vertices it has. Well, if you are, kind of quick-witted, you see that there's 3 here. There's going to be 3 over here, 3 over here, 3 over here, and then the other vertices are at the bottom. So it's really, this top is 12, this bottom is 12, so you have 24 vertices. Now, there's going to be other objects, like in the next example, that are a little bit trickier, that you can't quite just count them because maybe you don't see them all, or maybe there's so many that it would take forever to count. So here's what we would do for a normal kind of problem using Euler's theorem. Okay, so if we have 8 triangles, that means we're going to have 8 triangles which have 3 sides, right? And what we're going to be doing here, so we're going to do the same thing. We have 6 octagons, so they have 8 sides. So you have 24 plus, 48? And what we just did was we found how many edges there are for each type of shape, right? There's 3 sides and there's 8 triangles. There are 8 sides on an octagon and there's 6 of them. So this is how many edges, right? These are the edges that we have. If we add them together, we get 72 edges total. But look, isn't this, sorry, bad example. That was a bad choice. Isn't this double counted though for both the triangle and the octagon? So what we have to do is we have to divide it by 2 to eliminate the double counting. Right, so then this becomes 436. Great. Now we can finish the problem using Euler's theorem. Faces, it tells us it's 14, so 14 faces plus, I don't know how many vertices, that's what we're finding out. Edges we just found is 36 and plus 2, sweet. 38, that, and 14, great. Subtract 14 both sides, vertices equals 24, which is what we found earlier, right? So there's those technically 2 different ways, but you'll see in the next problem, we're not going to want to count them. All right. Uh-oh, a soccer ball. There's no way we're going to be counting this, so we're going to use Euler's theorem. 32 faces. All right, here's the 32 plus how many vertices equals the edges plus 2. So we just need to find the edges. There are 20 regular hexagons. So I'm going to do 20 times 6. That's hexagons, right? 12. Okay, so 12 pentagons as well, right? Here's the pentagons. Here are the hexagons. Never thought about that in a soccer ball. Some of you probably already knew because you play soccer. So pentagons is 5. So we have 120 on top. We have 60 on the bottom. We're going to add them up. You get 180. We're going to eliminate the double counting by dividing by 2. And we get 90. Oh, wow. You can't see that. I can't see that. Let's go to red. 90. Great. So now I can put 90 in right here, and now let's solve. 92 subtract 32, you get 60 vertices. Put edges over here. Great. And that is 11.4. Let me know if you have questions or things of that nature. But until next time, I will see you later.